So in the last of these part 1 videos, we're going to be looking at the factors that could affect our values for hydration or our values for lattice enthalpy. So remember that lattice enthalpy is a measure of the strength between oppositely charged ions. So whenever we're asked a question about a factor that affects lattice enthalpy, we must talk about attractions between oppositely charged ions. And the term that we use a lot in this topic is something called charge density. Now, charge density depends on not just the charge, but also the size. So you've got to think of it, charge density, as sort of how much charge have I got spread out over what volume, what size of thing I've got. So the bigger the charge, so the bigger the top number, the bigger the answer would be, but the smaller the size, the bigger the answer would be, because you divide by a smaller number, you end up with a bigger answer. So the smaller the size, the bigger the charge density, but the bigger the charge, the bigger the charge density. So let's have a look at size first. So what we're doing here is we're sticking to the same positive ion. So we're not looking at the factors affecting the positive ion, we're just looking at the negatives, chloride, bromide and iodide. They all have exactly the same charge. So the Na plus is irrelevant because they've all got that. And then we've got Cl minus, Br minus, I minus. So they've all got the same charge, they're all 1 minus. But as you go down group 7, there are more shells and more shielding, and therefore the size of the ion increases. So I minus is a much bigger ion than Cl minus. What is happening to the lattice enthalpy? And what we're looking at now is the size of the number and not the sign. So we are looking at the size, and the size is that they're getting less. So as we go down, they're getting less, but because they are negative numbers, we can't just say less, because actually on a number line they're getting higher, so we have to say less exothermic, smaller values. So why is that? So we would need to say as the size increases, so there's no change in charge here. So we might just write that charge is the same. If the size increases, the charge density, remember that size is on the bottom, charge density decreases. So if the charge density decreases, the attractions decrease. Therefore, the attractions between oppositely charged ions, that's what we're measuring, so the attraction between oppositely charged ions decreases, and lattice formation is less exothermic. Now if it was lattice dissociation, it would be less endothermic, because that's the positive ones. So as the charge density decreases, the attractions between oppositely charged ions decreases. What about if we change the charge? And we're going to look at this in 2 separate little sections. So we're going to first of all look at the comparison between Na plus Cl minus, Cl minus, and Mg2 plus with Cl minus. I'm going to look at that comparison first. So let's just compare those two first. NaCl and MgCl2. So what's changing? Well, magnesium is more highly charged, but it's actually also smaller. There's a big change here because it's smaller and more highly charged. So it's smaller and more highly charged. Therefore, stronger attractions will form, and therefore more energy is released on lattice formation. So it's more exothermic. So I'm going to pause the video and see if you can put that into a sentence. There we go. It's smaller and more highly charged, it has a bigger charge density, so stronger attractions. That's why it's going to be more exothermic. Let's have a look at the other two that we're comparing there. So MgCl2 with MgO2. So now the Mg is staying the same, but the chloride ion is becoming an oxide ion. Oxide ions are smaller than chloride ions. Chloride ions are bigger. Oxide ions are smaller and more highly charged than chloride ions. So our explanation is basically the same, but we now start it with oxide ions and comparing to chloride ions. So pause the video and see if you can write a sentence. So there we go. Oxide is smaller and more highly charged. Charge density is bigger, stronger attractions. If we go back, we can have a look. As we went down, it was becoming more exothermic, stronger attractions, more energy released. Okay, so we're going to move on and look at the factors that affect now, instead of lattice enthalpy, enthalpy of hydration. Remember, now we're not talking about oppositely charged ions. We must be really clear with attractions between ions and water, and if you get these wrong, that's where you're going to lose marks. But your answers are going to be very, very similar. It's just that you're not going to talk about oppositely charged ions. So have a look at these sizes. As we get bigger, charge staying the same, but size getting bigger, charge density will be decreasing, and these values are becoming less exothermic. So test yourself. Do you think you could come up with an answer? But bearing in mind that it's going to be very similar to the previous bit, but you mustn't write oppositely charged ions. We're now attracting water, not each other. So why would iodide ions attract water less than chloride ions? There you go. As the size increases, we've got the same charge. The charge density must be decreasing, and so the attractions to water are less. What about as our charge on our ion increases? But also bear in mind that as this charge increases, these ions are actually getting smaller as well, because going along the same period. So we've got the same number of shells and a similar amount of shielding, but more protons in the nucleus. These ions are getting smaller, so they're becoming smaller and more highly charged. How is their attraction to water changing? So they're becoming very much more exothermic. So why would aluminium ions attract water so much more than sodium ions? Again, pause and see if you can write your own answer. Okay, so as we're going from sodium to aluminium, charge increases and size decreases. So charge density is increasing a lot. Therefore, there are stronger attractions between the ions and water, and if there are stronger attractions, more energy is released. So if you even wanted to write that, you could. More energy released on hydration. As the two things come together, there's a big release of energy. And that is the end of this little section. So make sure that as well as being able to calculate enthalpies of solution from lattice enthalpy and enthalpy of hydration, you understand the factors that could affect the values of the lattice enthalpy or the enthalpy of hydration. So both values are affected by the same things, and so both will vary with size and charge, but we don't actually know if they'll vary the same amount, and so it's very difficult to predict that effect on enthalpy of solution except for by experiment.